Hello students, my name is Shayan Mitra. I am the faculty member of Department of Electronics and Communication Engineering of Greater Kolkata College of Engineering and Management. Today I am going to taking the class of Embedded System on Unified Modeling Language. Okay, this is the lecture number 35 and subject code is 704B. Okay, so let's begin with the lecture. Okay, so as we have already described in the earlier the class diagram, so in this case we have described here the class diagram, association, multiplicity. So here the multiplicity exactly 2, exactly from 1 to 4, at least 1 or 0 or more. Okay, 2 4 2 7 10 or more, default is exactly 1. So these are the association of multiplicity. So let's go to the next slide. Class diagrams. Association as class. Company employs person, and employees is a job. In with the employee there is a association of class where the, so company is an object, person is an object, and job is the another object. So the employees are connected to this objects named company, person, and job. In case of the class job, the associations are salary, function, and promotion. So these are the association of the class named job. Now now in case of company there is exactly one, now exactly one instance of class job per link. Okay, the lifetime of the association object is the same as that one of the link. So let's go to the next slide. Class diagrams. Associations, aggregation. Whole slash parts relationship is composed of an antisymmetric two forms: weak aggregation, simply aggregation; strong aggregation, and composition. Let's go to the next slide. Class diagram. Associations, weak aggregation. Weak coupling, sharing is possible. Lifetime of component is not dependent of composite. An instance of person may be employed by several companies. Okay, now an instance of person may be a part of several families. So one instance of a person may be part of several families. So this is the instance. Okay, and this is the instance for the object company. Now it's employees, all the employees are person. Now this is an instance of person, maybe both an employee and a family member. It means, now suppose this is the company class, it is been related, the employees are related to the to a person object and the company object. Now this specific instance, or can be, this instance person can be a family member, also can be a member of a company. So that is the example. So let's go to the next slide. Association, composition, strong coupling, no sharing. Lifetime of component usually starts and ends with composite. So this is the stock, this is the car. Here cardinality is at most 1, at least at most 1. Wheel, the instant name depending on the number, the wheel object has 4 different cardinality. Engine has 1 cardinality, body has 1 cardinality. Because if you are talking about a car name object, the this specific class has wheel named object which has 4 instances, engine name object which has 1 instances, and body name object which has a 1 instances. Okay, and stock has 0 to 1. So the stock object or stock basically related to the structure where we will have the count of number of object, or here the object is car. So now you could say that it has the composition of number of classes. So one stock is a class which is a composition of number of classes. Okay, so car is a specific class which has wheel named object, engine named object, and body named object. Now body named object got 1 instance, engine name object got 1 instance, and wheel name object got 4 instances. Now all these are connected to the number of stocks. So all these 3 things can be related to is related to the object name car, sorry, class name car. Now all these are stored in a stock name class where the number of cars are being stocked. So this is the composition where this specific stock named class stored all the classes of car. Okay, so let's go to the next slide. Class diagram often for the ATM. Now this is the card is inserted into an ATM interface. Okay, so we can use different, now the card name class got different number of cards. So that's why we have used the 0 dot dot 1 suffix here. Okay, so any suppose now one card is inserted into the ATM. Now this is the ATM interface. Okay, now ATM interface will be different for different ATM card. Now this depending upon the insertion, the session will be started. Okay, the session is connected to the customer information. The customer information is related to the transaction record. Now this transaction record class got n numbers of instances. Okay, because transaction record can be different for different card. Each card have different account number, different balance amount. So the instances will be different for transaction record class. Now this is related to the transaction, which is also a class diagram, where it also have a different kind of instances, because a transaction will depend on the condition that has been put forth in the ATM machine. Depending upon the amount you need, depending upon the inquiry you are doing, depending upon that, all the order instances will be different for transaction. And it will again go back to the session, and the session will be terminated. After that the card will be you can take out the card after the session is completed. So this is the whole diagram. That's why it is known as the class diagram. This is the class diagram of the ATM. Okay, so let's go to the next slide. Class diagram generalization. Now first, transaction, which has 4 different classes. Okay, now another is deposit, another is transfer, another is withdrawal, another is consult. Now each class has different number of objects, and each object got different number of instances. So this is the order: the class, the object, and the instances. So that is the order of the function. You can use the word generalized or generalized class diagram. This is the generalized class diagram. Let's go to the next slide. Now class diagram generalization, relationship between classes: no cardinality, antisymmetric, and transitive. Is a sort out substitutability principle. The subclass depends on its base classes. Support of generalization UML. Multiple inheritance is supported. Multiple classification indirectly or partially supported. Dynamic classification is almost not supported. Okay, let's go to the next slide. Now class diagram generalization, substitutability. B derives from A. Any instance of B is also an instance of A for any purpose of an A. Any instance of B may be substituted to an instance of A. B may add new properties to the ones inherited from A. Redefine operation inherited from A. B cannot get rid of properties inherited from A. Class diagram generalization, polymorphism. Now how the polymorphism works. Now suppose figure, drawing, ellipse, rectangle, figure, ellipse, rectangle, circle, square, all these are different objects. Okay, sorry, different class. Now each figure got different objects such as draw. Now figure, draw. Now in figure class we can draw different number of. Now suppose there is a we are talking about when you are discriminating between the classes. Now figure is a class, drawing is a class, ellipse is a class, rectangle is a class, circle is a class, square is a class. Okay, so each class got different objects. Now suppose figure is a class which got different number of drawings. So drawing is an object where we can have different number of drawing. Now each object can have different number of instances, because each drawing got different number of different components. So all these components are instances of specific drawing. Okay, now that is now if we differentiate between figure, it could be ellipse, it could be rectangle. Now in rectangle it's also a class which also have a different kind of drawing statement, which are objects. Now it is also related to the square. Now in case of ellipse is a class which has different objects like draw, and is also related to the circle, because circle as a class is also basically within the ellipse. Basically circle is a kind of an ellipse. So that's why what will happen, that the class circle will be inserted or will be a part of a subset of ellipse. Okay, in the same way the square, the subset square, basically square is a subset of rectangle. Okay, so in the same way the figure is related to the drawing segment. Okay, for all figure in components, figure draw. Okay, let's go to the next slide. Now multiple inheritance, how the inheritance will occur. Figure, now figure got ellipse, rectangle and triangle. Now ellipse got circle, rectangle got square. Now triangle got isosceles triangle, right angle triangle, and right angle isosceles triangle can also be divided in isosceles triangle and right angle triangle. So what will happen, the right angle isosceles triangle is basically inherited from isosceles and right angle triangle. Okay, now from triangle we get the inheritance of triangle or isosceles triangle and right angle triangle, and inheritance of isosceles triangle and right angle triangle is a common inheritance which is known as right angle triangle. The same will be considered here. Ellipse, in case of ellipse the inheritance is circle, inherited part is circle. In case of rectangle, the inherited part of rectangle is square, because we already know the square is a kind of a rectangle, and the same way the circle is a kind of a ellipse. Okay, basically when we are talking about ellipse, now ellipse, basically circle is a subset of an ellipse, so the circle is inherited from ellipse. Okay, the same way square is inherited from rectangle. The abstract classes and operation. Abstract class with no instance, usually at the top of a class hierarchy. Abstract operation, an operation without implementation, realization. An abstract operation makes the whole class abstract. If derived classes do not define the operation implementation, they are also abstract. Abstract figure. Okay, yeah, let's go to the next slide. The abstract classes and operations, the same examples are here. We have already described all this segment, so let's go to the next slide. That now abstract class is the top of a hierarchy, depending on the, these are the concrete class. This is the concrete class we already know. Okay, which are the defined. Now this is the abstract class where we don't know the specific figure. Now as we make a top to down approach, we will, as we are getting a top to down approach, what will happen, the abstraction will diminishes. Okay, now if we are going from down to, when you are going from low to high, the abstraction will increase, and as we go from low high to low, the abstraction will decrease. Okay, let's go to the next slide. Class diagram. Stereotypical classes. Entity class, long lived persistent information. This is the entity. Control class is coordination, sequencing and control. We use the control class. Boundary class, interaction between the system and its actors. This is the boundary class. Now stereotypical classes here again. Card which is inserted, ATM, we already know all this function, okay, which is the, now if you are if you compare this this slide with the previous slide here, now this is the entity class. Okay, it looks like this. When you're talking about control class, it looks like this. When you have a boundary class, it looks like this. Okay, so if we go to the next slide, here we have the card and we have the session, the transaction record, the customer information, ATM information. So ATM information is a boundary class, the customer information is a entity class, transaction record is an entity class. Okay, but session and transaction is a control class. So that is the stereotypical classes. So when we have this kind of a sign, when you have this kind of a slide, this sign is saying the control class, this sign is saying the what, boundary class, and this sign is saying this is an entity class. Okay, so let's go to the next slide. Now constraints of a class diagram. Restrict, clarify or specify the semantics of model elements, can be applied to any kind of model element. Constraints may be expressed by free text, special constraint language. Constraints are enclosed within the braces. Predefined constraints, types of constraints, stereotype, pre and post conditions, individual constraints. Class diagram. Constraint, class invariant, a condition that must be verified by any instance at any time. Adult, okay, condition that must be verified by any instance at any time. So adult is a class, age is integer, and is emancipated, it's a boolean. Class attribute, age. Now class operation is emancipated in there without side effects. Constraint stereotype, this is the constraint stereotype invariant. Constraint pre and post condition, person, married, boolean, gender, enum, marry person. So if you are now marry man, marry person, p. Now we will describe all the impact here. Pre not married and p gender not equal to married. Post married, pre who if it is pre then is not married, post it is then married. The operation contract, the precondition must be guaranteed by the client of the class. The post condition is guaranteed by the class itself provided that precondition holds. Okay, so let's go to the next slide. Class diagram. Constant class contract. Before an operation, invariance and precondition must be true. After an operation, invariant and post condition should be true. Now generalize and constraints. Ideally, a subclass should also verify its base classes invariance. Ideally, an operation overridden in a subclass may weaken the precondition and strengthen the post condition of its base classes. Demand less, promise more principle. So all these instances: class, object, instance. This is the hierarchy. Now if we go deep in the class different verification or variation, we will get the constraints of a class contract and other things. So this, as we are going deep, this is the basic way of using the unified modeling language. Okay, let's go to the next slide. Now constant class contract, the same here. Card dealer sell with a trade. Okay, pre old card less than 5 years old. This is the precondition, this is the post condition. For this specific class, we have another different condition. Okay, now for predefined constants: company, employees, person. Okay, unemployed agency. Now when the predefined constant is working out, this is an unemployed agency that is also related to the person. Now person class is related by a company and the unemployed agency through the link. The person and the company class is related through the employees link. Now the person and the unemployed agency class is related through the another link. Okay, the company, the person, the company employs person, the person manages the company. So this is the another link. So these are the predefined constants. Okay, let's go to the next slide. Now class diagram, best practices: avoid meaningless classes, no attribute nor operation, no significance with respect to the problem. At the analysis level, classes represent abstraction of the application. They are not a programming hack to reuse code. Round object, balloon, wheel, ball. These are the specific example of this total description. Avoid too big classes, many attributes, many operations, not all of them are needed at a given time. Too many responsibilities represent several abstraction. Use inheritance, aggregation, and association. Restaurant, number of meals. Okay, the same way. Now as we know, the restaurant use number of meals, so restaurant is related to table and waiter. Waiter got different number of waiters, it has different instances. Each table got patron. Okay, seat table, which is related to the table class. Okay, the card is a class which is related to the add dish. Okay, now this instant of the class this also different instances, which is basically a subset of the card class. Okay, so this is the example. Okay. Avoid explicit special operations: set, get, constructors, destructors, assignments. So avoid this kind of explicit special operation. Attribute versus association: use attribute notation for primitive non-object types. For object, prefers aggregation or even regular association with roles. Okay, car, color, string, power, integer. Owner is the person. Engine is also related to the car. We have already gave all these examples about. Avoid explicit circular dependency: base, bus. Okay, in particular, a base class should not depend on its subclasses. That's a very important point. Beware of the fragile base class problem. Okay, such as this: vehicle related to the engine and bicycle related to the vehicle. Base derivative. Okay. Do not confuse dependency and association. An association describes a relationship between instances. That's an important point. An association usually implies mutual dependency. Okay, so that's why it is important to understand the difference between the dependency and association. This implies the diagram on the left and but adds information related to the instances. Avoid redundancies. Do not represent the same information with two different ways. Attribute and association, redundant attributes. We already knows that man is a class which has my wife is a woman. Okay, so it is related to the wife, so there is no need to use the same redundant attributes. Okay, the same way the person, birth date, age is an integer. We already know that. At analysis level, avoid programming artifacts such as this: company, list of employees, person. Okay, now company, list of employees also violate previous slide advice. Okay, you can use this relation, and you can now when you're using this kind of relation, it is not required. There is no need to use the instances of a person, as we know, because the list of employees is basically the instances of the class person. So when you are already have the list of employees within the class named company, there is no need to use this kind of relationship. Okay, so that's the example. Let's go to the next slide. Now next subject we are going to discuss is realizing use cases and scenarios. Okay, so let's begin. Now in case of realizing use cases and scenarios, what we will going to use case realization as a collaboration, realizing scenarios, sequence diagrams, collaboration diagrams, interaction diagrams or comparison, activity diagrams and objects, and best practices. Okay, so let's begin. Realizing UC and scenarios. UC realization as a collaboration. List all the classes or roles that together realize a given use case. Allow traceability from use case model to class model. Okay, so this is the, so what you have to do, allow a traceability from a use case model to a class model. Okay, handle session, this is the transaction, ATM interface, customer information. Okay, these all are related to this specific class. Collaboration. Realizing UC and scenarios. UC realization as collaboration. Collaboration defines an interaction, a society of roles, objects or other elements to provide some cooperative and synergic behavior, possibly structural as well as behavioral, used to model patterns, design or analysis patterns. MVC pattern: model, control and view. Realizing UC and scenarios. Realizing scenarios. The requirement scenarios do not involve objects except for actors. There is a need to revisit the scenarios in the light of the analysis classes. The refined scenarios are part of the use case realization. Using formalism will make descriptions more precise, help to analyze the work. Scenario diagrams. Interaction diagrams, one scenario at a time. Sequence diagrams, collaboration diagrams, activity diagram and several scenarios, a full use case. Sequence diagram. Describe one scenario. Involve objects and messages. Messages exchanged between instances are called stimuli. A stimulus can be calling an operation with possible parameters. An operation is attached to a particular class. An operation call is a synchronous communication. A stimulus can be sending a signal. A signal is itself a classifier, a priori independent of classes. Roughly speaking, the instances of a signal are its occurrence. So what is it really means? It means, now suppose as I was saying, the first important part is message exchange between instances are called stimuli. Okay, first point. A stimulus can be calling an operation with possible parameters. An operation is attached to a particular class. An operation call is a synchronous communication. A stimulus can be sending a signal. A signal is itself a classifier, a priori independent of classes. Roughly speaking, the instance of a signal are its occurrence. Sending a signal is an asynchronous communication. Accent is on the time flow of events. Let's go to the next slide. Now this is the sequence diagram. Now how it works: customer, ATM interface, insert card, create session, ask PIN and goes to the customer again. Enter the customer, enter the PIN. So this is the acknowledging part and this is the input part and this is the acknowledging part. Now when the customer insert the card, it create a session. Now after the session is been created, it asks for the PIN. The customer, PIN, this acknowledged receipt is goes to the customer. The customer, according to the instruction, enter the PIN. When the PIN is accepted, as soon as the session got the information of the PIN of the customer, it goes to get/customer/information function is goes to the bank and it gives you the information. And during that information time, the session will provide you, as it is been noted, the session will provide you the display menu. Okay, so from the display menu, customer select the transaction process, which kind of transaction he is needed to require. Is he going to get a withdrawal? Is he going to get a balance inquiry? Is he going to change the PIN? So there are n numbers of options to fulfill for. So depending upon that, the customer select the transaction. So from that, the transaction process has been created. Okay, after the transaction is completed through the bank approval, it is goes to the display menu. Okay, it is goes to the customer's information, and after the session has been after the requested information has been shared, customer quit the session, and after the session is expired, the card is ejected from the ATM machine and the session has been completed. So that is the whole sequence of the diagrams. Okay, so we will end our lecture here at the sequence of diagram. We will continue this lecture and we will end this unified modeling language in the possible next session. Okay, thank you.